Buenas tardes a todos. Good afternoon, everyone. Tenemos hoy el honor de tener con nosotros al doctor Colin Alton del Wayne State University de Estados Unidos. Y pues si empiezo a leer el currículum del profesor Alton, no voy a acabar, pero voy a mencionar lo más importante. El profesor Alton tiene una licenciatura en física de la Universidad de Bristol de Inglaterra, una maestría en física de radiaciones en la Universidad de Londres y un doctorado en física en la Universidad de Londres. Resulta que el profesor Alton fue parte del equipo que diseñó y construyó el primer acelerador de uso clínica en el Reino Unido. El profesor Alton ha sido presidente de la APM, que es American Association of Physicists in Medicine, y también fue el editor en jefe de la revista Medical Physics, que es la revista de una de las más alta calidad en el área de física médica. Ha recibido diferentes premios a nivel nacional e internacional, como Award of Merit del International Union of Physics and Engineering, Science and Medicine. Ha recibido de Marie Curie Award International, de Marie Curie Award de la International Organization of Medical Physics. Actualmente trabaja en el área de braquiterapia de alta tasa de dosis. Él también es uno de los pioneros en el área de radiobiología, es decir, la manera para poder estudiar los efectos biológicos de la radiación de tal manera que el tratamiento que se hace en la clínica sea más efectivo. Este tipo de actividades es súper importante considerando los objetivos de la radioterapia, que es siempre tratar de matar el tumor, destruir el tumor, pero al mismo tiempo proteger a los tejidos sanos. Y eso requiere un conocimiento sobre el proceso de interacción de la radiación con la materia en diferentes tipos de tejidos y a partir de ahí determinar las eficiencias biológicas de los órganos. Y ahorita hay muchos de las nuevas técnicas de radioterapia en que los equipos ya están trayendo programas de modelos de radiobiología que permite hacer que los tratamientos sean más eficientes y que pueden tratar al paciente de una manera más exacta y precisa. Entonces le damos la bienvenida al profesor Alton y le decimos muchas gracias por aceptar nuestra invitación. This is an honor for us here at the Physics Institute to have you here. It was really important to us, and we are really glad that you accept our invitation. Thank you for coming.
Thank you. We get my slides up first. Wow. Please, can you hear me? Please excuse my voice. Yesterday I could talk, but I have a head cold and it got to my throat. Maybe you can read my slides. Maybe I need a lot of this. Or alternatively, tequila.
Yes.
Maybe I need some tequila. I tried it last night to see if it worked, but I fell asleep. Maybe if it doesn't come back, if it gets worse, you can get me some tequila. And if that doesn't work, get them some tequila. Get tequila in the audience. So I'm going to look at recent advances in physics. Clearly, for over 100 years, physics has played a major role in the development of cancer radiotherapy, from the invention or discovery of X-rays well over 100 years ago, radioactivity well over 100 years ago, and all the physicists that have been involved in utilizing X-rays and radioactivity. But I'm just going to look at the last 10 or 15 years, and then maybe a little bit, I'll look at the future of what's in store for us. So, what's the main role of physics in radiotherapy? The main role is to find physical ways to create ways to maximize the probability of cure, while at the same time minimizing the risk of normal tissue complications. It's very easy to cure cancer. You just put lots of radiation in, but then you're going to damage normal tissues. What does this mean at the cellular level? At the cellular level, this means minimizing tumor cell survival and maximizing normal tissue cell survival. This is a radiobiological problem, but it involves physics. So what are the radiobiological issues that we face? Doses that are high enough to kill all the cancer cells, as I said, in a patient's tumor, are often too high for the surrounding normal tissues to tolerate. Tumors often contain some cancer cells that are resistant to radiation. For example, normal tissues are all well oxygenated, and oxygen is the most powerful radiosensitizer that we have, whereas some parts of a tumor are typically poorly oxygenated and therefore less sensitive. And there are other reasons why. Some cancer cells are less sensitive than normal cells. We are stuck. Okay. It's slow. First, let's look at cell survival. Cells will die if their DNA is permanently damaged, so as to prevent them from replicating. That's what we're trying to do in cancer radiotherapy. This occurs typically when both arms of the double helix are damaged, which we call a double strand break. And this is what it looks like. Each strand of DNA has matching genetic information on both arms of the DNA. So if you have a single strand break and the other strand is not broken, where you've got duplicated a mirror image of the genetic information, then this is usually repairable. It can be repaired by copy and pasting the genetic information from the intact arm. Whereas a double strand break, you've lost this information, so you've lost the data. So now that will be unable to replicate. So double strand breaks are what cause permanent damage to cells. What's the effective dose on this? Well, at low doses, 2 DNA strand breaks are unlikely to occur. So single strand breaks will dominate and repair is common. So at low doses, it's easy for cells to repair. At high doses, double strand breaks will become more common, so there will be less repair. So what this means in terms of survival curves is that they get steeper as the dose increases. So here's a survival curve of cells. And you can see it gets steeper as the dose gets higher. So for instance, you can go maybe 3 orders of magnitude in cell survival for a dose of the order of 10 gray. But we need to be concerned about both normal cell survival and tumor cell survival. Cancer cells, it turns out, do not repair damage as well as normal tissue cells. And that's the basis of radiotherapy. That's why radiation cures cancer, because the cancer cells don't repair the damage as well as do normal cells. Survival curves will be straighter for cancer cells because they don't repair the damage as well. It turns out it's what I like to call the window of opportunity at low doses where the survival of late reacting normal cells exceeds that of cancer cells. Let's look at that in terms of a cell survival curve here. What we see is the cell survival curve for cancer cells in red is not as curvy as the cell survival curve for late reacting normal tissues. So you've got the green curve is for normal tissues, and the red curve is for tumor cells, cancer cells. And you'll see there's this window of opportunity at low doses where you can get a higher number of cancer cells killed than normal cells killed. That's what you want to do. That's the whole basis of radiotherapy. Unfortunately, you can see that you can only get down to about 2 orders of magnitude in cell survival before the opposite is true, and you're killing more tumor cells, more normal cells than you are killing cancer cells. So, question is, typical tumors contain about 10 to the 8 cancer cells. Does this mean that since you cannot get more than about 4 gray, or you will kill more normal cells than cancer cells, and 4 gray is not nearly enough to kill 10 to the 8 cancer cells, you can never cure cancer by radiation? Well, no, because we've learned well over 100 years of clinical experience that you can fractionate the doses per fraction within this window of opportunity. For instance, at about 2 gray per fraction. So the vast majority of cancer radiotherapy over the last 100 years has been at about 2 gray per fraction. And that's clinical practice. You learn by practice. When they first started radiotherapy, they tried giving higher doses per fraction. Didn't work. You damaged too many normal tissues and you couldn't get cure. So we've learned by clinical experience to work in this window of opportunity of about 2 gray per fraction. And this is what cell survival curves look like at about 2 gray per fraction. These are the 2 curves we looked at earlier. This is if you give 2 gray per fraction, and you can see that you get more survival of the normal tissue cells than the cancer cells. So now we can go to high enough doses and separate these curves out. We can kill enough cancer cells without destroying too many normal cells. That's because of fractionation. So you've got this window of opportunity, but note that in that curve, I assumed that the normal cells were getting the same dose as the cancer cells. I just had dose on the x-axis. So they got the same dose. But is this a reasonable assumption? Well, it used to be. Before we had conformal radiotherapy, for many decades, the normal tissue sometimes the normal tissue got more dose than the cancer cells because we didn't have high enough energy radiation. But is that true now? No, it's not true now because we're using physics, come back to physics, to optimize dose distributions to keep the dose to normal tissues less than the dose to the tumor. So what does that mean in terms of cell survival? It means that the effective dose that the normal tissues are getting will usually be less than the effective dose the tumor is getting. So there's a thing called geometrical sparing of normal tissues. So, and we can define the effective dose as the dose if we delivered it uniformly, we'll get the same rate of change, if it might be tumor control or normal tissue damage, as if we give it with an inhomogeneous dose distribution. So we can define a geometrical sparing factor, which is the effective dose to normal tissues divided by the effective dose to tumor. And for modern day radiotherapy, F is going to be less than 1 because we apply physics to get the right dose distribution. And we're getting better and better at it, and we're getting lower and lower values of this geometrical sparing factor. So let's give a very modest geometrical sparing factor here, a 20% sparing of normal tissues, and let's see what happens to this window of opportunity. Well, you can see the window of opportunity increases tremendously, and it goes up to, just with a 20% sparing of normal tissues, we're now going up to doses as high as 10 gray. So we've widened the window of opportunity for our cancer radiotherapy. So what does this mean? Well, it means with optimal physics, we can safely use much higher doses per fraction. For teletherapy, we can use hypofractionation, more than 2 gray per fraction, considerably more than 2 gray per fraction. And I'll come back to that in a minute, some examples of that. For brachytherapy, for radioisotope therapy, we can now use high-dose rate brachytherapy, and both of these are being widely used now throughout the world. And it's because of physics, because we now have more conformal radiotherapy. So I spend quite a bit of time talking about developments in these fields. What about other biological factors before we talk physics? Are there any other biological factors we need to be concerned about that maybe physics can help? Yes, repopulation of cancer cells during a course of treatment. While we're treating a patient during a course of treatment, typical course of treatment might be several weeks, maybe even months. The cancer cells are continually dividing and trying to outpace us, grow faster than we can treat them. So this is repopulation of the cancer cells. So the shorter the course of treatment, the better. And there's also, what I mentioned before, is radioresistance of some kinds of cells like hypoxic cancer cells. They're more resistant, so somehow we have to overcome that resistance. And yes, we can. We can use high LET radiations. And I'll spend a little bit of time talking about high LET radiation. High LET radiations produce more double-strand breaks directly because of the density of the ionization. And they don't care about the presence of oxygen or the absence of oxygen. You get the same, pretty much the same effect. So I'll talk a little bit later on about high LET radiations in radiotherapy. So let's first of all look at hypofractionation. Hypofractionation, the use of fewer fractions at higher doses per fraction. So higher than about 2 gray per fraction, where we've had all this experience. Hypofractionation is the use of higher doses per fraction. Typical doses per fraction, depending on number of fractions you use, range anywhere from 3 to 20 gray. And the number of fractions go from anywhere from 1 to 20. That's what we call hypofractionation. So what do we know about hypofractionation? Well, we know because we've done lots of clinical trials over the last 15 years that hypofractionation works just as well as conventional fractionation, providing we use physics to optimize the dose distributions, so that we can cure the tumor and avoid normal tissue complications. So we're now going to use more and more hypofractionation. So my prediction is, with optimal use of physics, using more sophisticated, and I'll go over these in a moment, more sophisticated imaging, image guidance, motion tracking, protons, heavy ions, we will be using as few as 5 fractions for most cancers in the relatively near future. What will that mean? Well, first of all, treatments will cost less. You're giving less fractions. It's more convenient to give less fractions to patients. It's more convenient to the patients and the staff. With fewer fractions, the overall time for a course of treatment can be reduced, and this reduces repopulation as well. So you're having the effects on repair, and you're having the effects on repopulation. And of course, hopefully, cure rates will actually increase because you're doing all of this because of sophisticated applications of physics. And hundreds of physicists around the world are working on continually improving the physics of radiotherapy to get better and better, and my anticipation is that cure rates will increase because of this. What are the recent advances we've made to achieve this goal? Well, physicists have created ways to accurately visualize the shape and extent of the tumor and surrounding tissues, not only before treatment, but even during treatment. So you can now visualize the organs at risk that you want to avoid and the tumor during the treatment itself. And one of the things we call this is image guidance. The image that you're getting guides the treatment. Also, to make the high-dose region conform to the shape of the tumor and avoid normal tissues, and we call that highly conformal radiotherapy. And then finally, to minimize the risk that the tumor will move out of the high-dose region during treatment, and we call that motion control and motion tracking. So let me go over some of these. What have physicists done in the last 10 years to improve these? So let's first of all look at image guidance. We've used CT for a long time. For 30 or 40 years we've been using CT, but now we're using it in combination with magnetic resonance imaging and positron emission tomography for planning treatments. We've done all that before, but now we're combining them into our treatment plans altogether. This will help us to better delineate target volumes and surrounding normal tissues. And we're using these to guide our treatment planning. We use CT and/or MRI and/or PET and a combination of all three to guide our treatments during the treatment. We now have linear accelerators with onboard CT images, either the regular CT images at kV energies or megavoltage using the actual radiation beam that we're going to treat the patient with megavoltage energy CT. We now have magnetic resonance linacs, so we've got linear accelerators to treat the patient. In the same gantry, we have an MR unit, and we also have PET CT linacs. So an MR linac looks just like an ordinary MR unit. It's got this usual aperture here for the slide the patient in, but generally with the MR linac system, you need more distance here for the linear accelerator to treat the patient. Typically, you want distances from the target of the linear accelerator to the patient of about 1 meter. So now this is much bigger than a typical MR unit. But this is what an MR linac unit looks like. It's a combination of MR. A lot of physics. Years and years and years of physics development has had to go into this. It sounds simple, but it's not simple, because how does a linac work? A linac works by moving electrons. It accelerates electrons to hit a target. Well, having electrons with magnets is a big problem. You've got this magnet trying to do something else, trying to create an image. At the same time, you're trying to move electrons. So a lot of physics involved in combining an MR unit with a linear accelerator. There's a new PET CT linear accelerator being developed. This is going to be available soon if it's not already. I've seen it at exhibitions. I don't think they've sold any yet, but it's coming very close to selling. And what this is, you've got a regular linear accelerator, you've got a PET scanner, and you've got a CT scanner all in one unit. You can observe what's going on in the patient while you're treating that patient. Very exciting development. And combining all these things together is actually used today you can start off, for instance, with fusing your PET and MRI, and we've seen a few examples. Those have been in the course so far. A few examples where this is being done now. Why would you want to do that? Well, because you get different information in a PET scan and an MRI scan. Fuse them together, you can visualize the tumor much better. And then combine this with fusing the PET and MRI image with a CT image. Why would you want to do that? Well, a CT image has better information about the exact positioning of everything inside the patient, whereas there's some distortion and loss of resolution when you're using PET or MR. So you need to use the CT for the geometrical shape of the patient and positioning of everything. So combine them all. Typically now we're doing this, but now we're going to be able to do it live on the patient while the patient's in the radiation beam. Let me talk a little bit about what's been done in highly conformal radiotherapy. We've been working on this for 50 years, trying to make radiation beams conform to the shape of the target that you're trying to treat. It's really only come to fruition in the last 10 or 15 years in a big way. So it's not new, we've been doing it a long time. The major breakthrough came with the availability of linacs with multi-leaf collimators. I remember many years ago we were trying to do this without multi-leaf collimators, and it was very difficult and didn't really work. And then computer control, of course, capable of modulating the intensity across the radiation beam. These things have only really been available in the last 20 or 30 years. So we were able to develop what we call intensity modulated radiotherapy, IMRT. It was the technology developed by physicists, and it began to receive widespread use in the last 10 or 20 years. Maybe, I don't think more than 20 years commercially. Individual institutions doing research in this could do it, but most institutions were not able to do it. Here's an example just to show you what a 9-field IMRT treatment would look like. We're firing 9 fields into this patient's prostate, and each field has its intensity modulated, so it has very complex design of the actual field itself. Clearly we couldn't do this before we had the computers that could do it, first of all, and have the multi-leaf collimators that were capable of doing it. So it's only been possible to do this over about the last 20 years. So the intensity distribution within each of these fields is designed by inverse planning. So the planner tells the computer system, the optimization system in the computer, what you want. This is the distribution I want. And then the computer goes through hundreds of iterations to decide how best to do that with each of the radiation beams surrounding it. So, and a variety of inverse planning algorithms have been devised over the last 20 years by physicists. It's a big physics revolution, if you like, in the treatment of patients. This is probably the biggest change that was made in treatment of cancer patients over the last 20 years. And then since then, physicists have developed more efficient ways to do this. For instance, intensity modulated arc therapy. So now you're actually doing IMRTs with beams that are moving through specified arcs, and volumetric modulated arc therapy, VMAT, where it's the next step up. You're simultaneously moving changing the aperture shape, gantry rotation, the speed of the gantry rotation, and dose rate. And the patient's moving while you're doing all this on the couch. So all of this has made the whole system more efficient. Both of these result in reduced beam on time compared to conventional IMRT. We've also developed special linacs and linac technologies to shape the radiation beam to the shape of the target that you're trying to treat and to avoid the normal tissues. For instance, tomotherapy, that was that is a 6 million volt linear accelerator that's rotated around the patient lying on the couch while the patient is moving. So the machine's rotating, irradiating the patient, and the patient's moving. It's actually very like spiral CT. In the imaging field, you've now got spiral radiotherapy. And that has an advantage also that you can do megavoltage CT imaging. You can actually get, since it's just like a CT unit, you can create CT images with a megavoltage beam with tomotherapy. And the beam is modulated continuously while all this is going on. And then there's also the Cyberknife, which is a 6 MV linac also mounted on a robotic arm, and that actually paints the dose distribution that you want in the patient. So it's almost like painting from every angle in 3D, because now this is on a robotic arm. You can do it 3D around the patient, and you have imaging set up on those patients too at the same time. So let's look at tomotherapy. It's what a modern tomotherapy unit looks like. When I first saw tomotherapy, it didn't look like that at all. This is what it looked like when I first saw it at the University of Wisconsin in Madison. And this is Rock Mackie, who invented the tomotherapy unit. And I don't think I took this picture, but it was certainly about that time when I was visiting University of Madison. I had a lot of reasons to go there. One, it's a very good school and lots of good physics there. But also my son was working there with Rock Mackie. My son's a medical physicist. And he was working with Rock Mackie, doing a lot of the preliminary measurements on tomotherapy. So I learned a lot about what had to be done to get this whole thing working. And now there are hundreds and hundreds of tomotherapy units around the world. And then the Cyberknife, just show you a quick picture of schematically what a Cyberknife looks like. The Cyberknife has the usual couch, but it has a linear accelerator mounted on a robotic arm that can move around in 3 dimensions around the patient. And it has X-ray tubes and imaging devices so that you can take pictures of the patient while you're actually doing the irradiation of the patient. You can actually follow. So if the patient has a lung cancer, for instance, you can follow the lung cancer as the patient's breathing, and the robotic arm can be programmed to move and keep, again, paints the radiation dose in a moving target. Again, another major physics development. What about motion control? Well, the simplest form of motion control is to stop the patient breathing. I'm treating a lung cancer patient. I tell the patient to breathe in and hold the breath, or breathe out and hold their breath. Not a lot of physics involved in that, a little bit, but not a lot of physics involved, very uncomfortable for the patient. So for lung cancer treatments, there's no movement while the beam is actually turned on. So you turn the patient, you tell the patient to stop breathing and irradiate them. Maybe you give them a rest partway through. Better still, and now involving some physics, is gated treatments, where you actually gate the treatments so they follow the breathing cycle of the patient. So you need something on the patient or in the patient to show the breathing cycle, and you modulate the beam. You have the beam turned on when the patient's breathing in, for instance. When they breathe out, the linac turns off, and then back again. So you're gating it to the treatment. Much easier for the treatments to do that, but obviously a lot more physics involved. And then you can actually track, you can monitor the patient and track the patient's motion, and the Cyberknife was an example of tracking the motion of the target while you're actually treating it. And then, of course, shorter treatment times are going to help motion control. The shorter the treatment time, the less likely it is that the patient's going to be moving around. So that will help considerably. And I'll talk a little bit about how we can use physics to shorten the treatment time. One of the developments in shortening treatment time is with flattening-free linear accelerators. So I'll talk a little bit about flattening filter-free FFF linear accelerators, a fairly recent development by medical physicists. What do we mean by flattening filter-free linacs? Well, when the X-ray beam emerges from the target of a typical linac, the intensity is much higher in the center than at the periphery. It's much more forward guided because of how the interaction produces X-rays from the target. So the target, the forward motion of the X-rays is greater near the center than it is in the periphery. Most linacs are equipped with flattening filters to attenuate the central part of the beam so as to create a more uniform profile. So the flattening filter is a cone, and the center is a lot higher than the edges. So you actually absorb a lot of the beam in order to flatten it. So why do we need a uniform beam profile? Many, many decades went by, we used uniform beam profiles. We used flattening filters, and we still use, in most linacs, they still have flattening filters. Well, we use them because it simplifies measurement of the beams. It's much easier to measure a beam if it's flat than if it's sharp in the middle, if it's much higher in the middle than at the edges. Treatment planning and combined multiple beams are much more simple if you've got flat beams. Much easier to do that. Delivery of the treatments. It's much easier to deliver the treatments if the beams are nice and flat. They're the same from the center out to the edges. So why are flattening filters no longer necessary? Well, first of all, we routinely use non-uniform beams, for instance with IMRT. So why start with them flat if we're going to make them non-uniform? So you don't need to start them flat to make them non-uniform. They can be non-uniform, and then we make them non-uniform in the pattern that we want them to be non-uniform. So we don't need flat beams anymore to treat the kinds of fields that we're currently treating. Treatment planning computers are now much more sophisticated than they were 20 years ago. They're capable of planning non-uniform beams instead of just uniform beams. Beams no longer need to be simple in order to be measured and entered into the treatment planning computer. We have very sophisticated ways now of measuring radiation beams. No need for them to be relatively flat anymore. It doesn't matter. Modeling of beams, for example, by Monte Carlo is now routine. We do it all the time. And we can do it just as easily with a flattening filter-free beam than we can with a flattened beam. Computerized linacs are now able to produce complex beam arrangements with flattening filter-free geometry, with no flattening filter in. So what are the advantages of flattening filter-free linear accelerators? Well, dose rates are higher, so treatment times are considerably shorter. The flattening filter absorbs a lot of the radiation beam. If you take that away, now you've got much higher dose rates, maybe of the order of 10 higher dose rates. So your treatment times can be shorter. More patients can be treated in a day. So it's more efficient, it's less expensive. You reduce the treatment costs. You can eliminate absorption and scatter that takes place in the flattening filter. A lot of absorption takes place, we talked about that, but a lot of scatter takes place too. And by the way, a lot of scattered neutrons. You generate neutrons from a higher energy beam, and they get scattered out, and you've got to do something about those. They go to the patient, and they try to get out of the room and go to the staff outside the room. So you can eliminate a lot of that. It simplifies the design of your treatment room. Now you don't need as much shielding for neutrons or as much shielding for scattered photons as you needed before. And the patient whole body dose is now reduced because there's no scattering from that flattening filter into the body of the patient. You have a pregnant patient, for instance, it's very difficult we physicists who have tried to do it, it's very difficult to keep the dose down to the fetus while still irradiating the tumor in the patient to a sufficient dose. It's a little bit easier when you've got flattening filter-free geometry. So you've got lower risk of radiation-induced cancers, both to the patient and to the staff outside. Let's look a little bit about highly conformal radiotherapy using heavy charged particles. Why can we do highly conformal radiotherapy with heavy charged particles? For instance, with protons and with heavy ions. Well, it's very simple. With protons and with heavy ions, it's due to the Bragg peak. So, that's interesting. I've lost half of my picture. Well, I've lost half of a picture here, sorry. I'll describe it anyway, no problem. With protons, I think all physicists know that missing here, you've got a Bragg peak. So this is the dose against depth in the patient, and you get to a certain depth, and you get this Bragg peak where the density of ionization is much higher. Well, that will produce more dose, so dose is much higher. But secondly, it will produce, because it's got a higher LET, it will produce a more biologically effective dose. Because now, we talked about oxygenation of tumor or lack of oxygen in tumors. Now it doesn't care. In that Bragg peak, the damage to well-oxygenated cells and the hypoxic, poorly oxygenated cells is about the same. Doesn't make any difference. So that's an advantage. The problem with protons, and we'll see in a minute, heavy ions, is that tumors aren't that small. The only tumors I know where protons are used that are that small, that are as small as the width of a Bragg peak, are ocular melanomas. And we've been treating with protons for ocular melanomas now for over 50 years. But that was the only application, because you could get the advantage of the melanomas are resistant to radiation. They're known to be a cancer that's pretty resistant to radiation, but at high LET, in the Bragg peak, they're not that resistant to radiation anymore. So protons have been used quite extensively in some institutions for the treatment of ocular melanomas. The problem is that unseen in this diagram, this axis down here, in order to, if this is the tumor, in order to get to the tumor, you're going to have lots of Bragg peaks that sum up to what we call the spread out Bragg peak. So what we do is we create different energy proton beams from the highest energy, which corresponds to the deepest part of the cancer, to the lowest energy that corresponds to the shallowest part of the target that you're aiming for, and you combine them. So you might combine 10 different Bragg peaks. The problem with doing that is that the biological effectiveness here is totally different from the biological effectiveness in the Bragg peak. And you lose most of the advantage, the biological advantage of heavy charged particles. So in theory, something like 10% a proton beam used in practical radiotherapy is only about 10% more biologically effective than typical X-ray beams. So there's not much of a biological advantage because you spread out the Bragg peak. Oh, no, we've lost it. I don't know why we've lost it. Don't worry about it. Oh, you're trying it? Let's try it. No, we still lost it. Okay. So the major rationale of proton therapy is the Bragg peak. You get a beautiful dose distribution because the dose beyond the Bragg peak, and I think that probably, yes, that came up. This is what happens when you treat with X-ray therapy. There's a beam coming in here, and X-ray therapy, after you pass through the target, you still get quite a dose beyond the target. With protons, once you've passed through the target and you've set your Bragg peak, your depth of the Bragg peak, the highest energy Bragg peak at the depth, the maximum depth of the target, there's no radiation beyond that. So this is a big advantage in terms of conformal radiotherapy. You can now use radiation beams of protons coming from different angles, and you'll get rid of this dose beyond the Bragg peak. So in theory, you can get better dose distributions with protons than you could possibly do, even with highly sophisticated IMRT methods with photons. And that's what the proton protagonists tell me, that they claim that you can get a better dose distribution. Maybe we'll talk a bit about that later on. So, is anybody using proton therapy? Well, it turns out there are about 92 proton therapy facilities in operation today worldwide, and 45 are under construction. So this is expanding rapidly. Why isn't it expanding quicker? Well, it's not expanding quicker because they're very expensive. Typical proton therapy facility will cost maybe 10 times more than the typical X-ray therapy facility with linear accelerators. So it's much more expensive. But if the advantages are greater, then you expect these to expand more. And you can see there's a pretty rapid expansion. 92, 45 are already under construction. About 200 clinical trials are going on right now, looking at the biological effect of the clinical effectiveness of proton therapy. About 200,000 patients have already been treated worldwide. So it's not really widespread, because if you looked at these numbers for photons, this would be tens of millions of patients have been treated worldwide. So it's still small compared to photons, but it's rapidly expanding. It's expanding much more rapidly than linear accelerator therapy. What about carbon ion therapy? Well, there's a typical carbon ion therapy unit. I think this one's in Heidelberg. I actually sent a friend of mine there who lives close to Heidelberg. He had a prostate cancer. And I said, why don't you go and see if they'll treat you? They couldn't treat him because they had such a long waiting list, because there were so few of these facilities worldwide. In fact, one of my PhD students was running this lab at one point. He's now back in the United States. So he specialized in carbon ion therapy. There are currently only about 13 of these facilities in operation worldwide, and only about 5 of them are under construction. Why? Why so few? Well, because now you're talking about 100 times more expensive than conventional X-ray therapy. So they're very expensive. Why are we doing it at all? We're doing it because with carbon ion therapy, even in the spread out Bragg peak, the biological advantage of carbon ions is so much higher than it is for protons that you still have a considerable biological advantage. So for certain types of cancers that are typically known to be resistant to conventional treatment and to proton therapy, you can treat. So prostate cancer wasn't going to be treated there. There's no way my friend was going to get treated on this machine. I didn't have any influence. I couldn't persuade him to do it. I'm sure that he will get superb treatment for his prostate cancer, because you've got the Bragg peak advantage, you've got the physics advantage, and if there are any resistant cells there, you've got that biological advantage too. So about 30,000 patients have been treated so far with heavy ions worldwide. They are expanding. So there are 5 facilities being developed, and probably there will be more, especially if they start publishing very significant improvements in the clinical results that are achieved for otherwise resistant cancers. So let's look at these graphically. We've got proton therapy expanding very rapidly from rather recently, and it's accelerating. Similarly with carbon ion, or what we typically call heavy ion, but it's nearly all carbon, not all carbon ion, nearly all carbon ion therapy is increasing quite rapidly. So what else can physics do to improve radiotherapy? We can modify the radiation so as to increase the sensitivity of cancer cells relative to normal cells, or increase the tumor dose. For instance, we can use high LET radiation, which I've already talked about, and that's expanding. This is an added advantage, as I mentioned, of carbon ions over protons, so we're doing that. There's a new one. This hasn't actually been put into clinical use yet. It's coming in the next 5 years. We can use ultra-high dose rate radiation to reduce normal tissue cell death. This, I'll show you some examples. This has an advantage. Very, very high dose rates of conventional radiation will have less effect on the normal tissue cells compared to the cancer cells. It's got a biological advantage. Or we can add agents to tumors and increase the dose to the cancer cells. And we heard a little bit about, those of you who were here yesterday, with using X-rays instead of megavoltage X-rays, kilovoltage X-rays, to patients that have iodine contrast agents in their cancers. So that's one way that this can be done. I'm going to look at a different way of doing exactly the same thing, where quite a bit of research is going on. So let's look at this ultra-high dose rate. This is what is now called flash radiotherapy. Ultra-high dose rate, flash radiotherapy. Animal experiments have shown that treatments administered in a single short pulse, a very high dose rate. This is about 100 times the dose rate that we typically use for our patients. And you can see some advantage of this already. But irradiating the patients at 100 times the dose rate, we don't need to beam on very long, so we can treat a lot more patients. So we'll look at that in a minute. And we see from animal experiments that normal tissue cells have far less damage than the same dose administered at conventional dose rates. So let's have a look at that as an example. And by the way, look at the dates on all my references from now on are going to be pretty current. This hasn't, this was published just last year, and they're looking at fibrosis in the lung, in this case of mice, fibrosis in the lung as a function of weeks after irradiation. So you irradiate it here, and then you follow fibrosis in the lung for several weeks afterwards, almost a year afterwards. And what you see is that at conventional dose rates, at the dose that was given to these mouse lungs, got considerable fibrosis. Whereas at these flash dose rates, extremely high dose rates, you can see much higher, 2,000 times higher than this dose rate. You're getting much less fibrosis. The same dose gives less effect. And the question now is, can this be done in practice? This is great in the lab with mice. Can you really do it in practice? And the answer is yes. A clinical linac has been successfully modified to produce ultra-high dose rates, high enough for flash irradiation. And again, this isn't even published yet. It's in press. You can actually get a copy of this online only, but it hasn't hit print yet. So I managed to get a copy of it, and they've done it successfully. They've actually treated a lot of medical physicists here in the audience. If you go to the International Organization for Medical Physics, IOMP website, iomp.org, and look at the very latest newsletter that came out yesterday, you'll find that they talk about flash irradiation. They give a lot of references to flash irradiation, and they have a brief description of what it is and maybe some of the explanation of why it might work. So have a look at that, iomp.org, the very latest newsletter, the July newsletter for this year. What are the other benefits then of this very rapid irradiation? Well, there's no motion during treatment. Typically, the treatment takes far less than 1 second and it's all over. So you tell the patient, hold your breath, whoop, it's done, it's all done. Can reduce margins. If the target's not moving while you're treating it, you can reduce the margins. You don't have to take into account that it might move around just a little bit. It's not moving at all. It can't move in that short period of time. So less normal tissue needs to be included in the high-dose volume. Much shorter treatment times mean more patients can be treated per day. So if we can get this going, and I suspect in the next 5 years we will get this going, some of the big linear accelerator companies are going to jump on this and say, this is great. We can do this. We've been shown how to do this on a commercial linear accelerator. We can modify our linacs accordingly. It's going to be a lot of physics needs to be done if we start doing this, because now our dosimetry is going to get pretty complicated when you're using very short pulses like this. Increased utilization of facilities, decreased cost per patient could be very important to do this. Now, can we add things other than contrast agents that we heard about yesterday? Can we add things that go to tumors that will increase the dose to the cancer cells? So this is, again, really physics. We're increasing the dose by putting something in the cancers that will give you a bigger dose to the cancer, but not to the normal tissues, because they don't go to the normal tissues. High atomic number nanoparticles can be used to increase local dose. There's been quite a lot of work done on doing this. Nanoparticles get trapped in the tortuous tract. We had a talk earlier today about what happens to the microvascularity inside a tumor. It gets all muddled up and messed up, and the blood vessels have a very, very tortuous tract. And here's a simplistic picture of that. This would be a typical blood vessel in a patient, or in a normal tissue in a patient, in an organ in a patient. This is what happens diagrammatically, what happens when the cancer starts getting in there and causing lots of damage and reorganization of the microvasculature inside the cancer. And these nanoparticles get trapped in there, depending on the size of the nanoparticle, gets trapped inside there. So now we can trap nanoparticles, and it's all a matter of timing. You inject these into the patient, then you wait until they've got trapped in the normal in the tumor, and they've been removed from the normal tissues, and then you do your irradiation, and you'll get an enhanced effect, because these are high Z particles, high atomic number particles. So how do X-rays interact with high atomic number particles? Well, we all know, all physicists know, this is photoelectric effect, and it's a very significant function of the atomic number. The photoelectrons will increase the dose close to the atomic number materials, but even more importantly, the Auger electrons, which are released when these electrons are removed, then interact either in the high Z nanoparticle or just outside the high Z, in the tumor, just outside the high Z nanoparticle. These are very low, as you all know, Auger electrons are very low energy electrons. They're typically absorbed locally, and they won't reach the normal tissues outside of the tumor. So they'll increase the physical dose to the cancer cells without increasing the dose to the normal cells. And as I'll explain later, also because they're such low energy, they're high LET. So you've actually got a high LET advantage at the same time. So the Auger electron process, I shouldn't even show you this because you're all physicists. You all know what happens with Auger electrons. You get an electron released, and the Auger electron shower occurs with the energy that the atom has now gained, goes to an electron and knocks the electron out. So you get a whole shower of Auger electrons coming out. So these increased vacancies create an Auger cascade. So you get lots of these Auger electrons, some higher energy than others. Some will get absorbed within the nanoparticle, so they're not any use at all, they're wasted. But if the nanoparticle is small enough, then they'll get out of the nanoparticle and radiate all of the DNA that's just inside the tumor, but outside of the nanoparticle. So Auger electrons are produced. Ferrector interactions were within the high Z nanoparticle. They're absorbed within the nanoparticle itself, so they're wasted. The smaller the nanoparticle, the fewer of these Auger electrons are going to be wasted. So the size of the nanoparticle is very important. Lots of physicists are involved in looking at optimal size of nanoparticles for enhancing the effect of the radiation. What are the additional benefits? As I mentioned, they are high Z. If they're high Z, then they're very good for X-ray imaging. X-ray imaging of high Z materials is great. So they can be used for imaging the cancers. And in fact, you could use the images of the cancers to work out the density of high Z materials, so you can work out the dose enhancement from the density of the high Z materials that have got trapped inside the tumor. So you can use them for that for dosimetry too. The electrons I mentioned before are high LET, so they have all the advantages of high LET radiations. This could increase the effect on resistant cancer cells like hypoxic cancer cells. Well, there are lots of questions about high Z materials. The biggest one is, okay, this works very well for kilovoltage X-ray because kilovoltage X-rays interact Z to the power 4. But you don't get that advantage, you don't get the photoelectric effect with megavoltage energies. So will it work with megavoltage energies? Is the increased LET of the radiation from the Auger electrons enough to increase the effectiveness of linear accelerator treatments, for example? Can an increased effect on hypoxic tumors be demonstrated? And here's a model of breast cancer radiotherapy. And what we're looking at here are the survival of different types of cancer cells at different energies, 150 kilovolts. Yes, there's a big advantage. The tumor cells, the cancer cells, suffer more than the normal cells. But if you do this at 4 MV, there's still a bit of an advantage. And do it at 15 MV, there's still a bit of an advantage. Could be a very significant advantage. You're talking about of the order of a factor of 2 in cell survival. And it's free. You could use these nanoparticles to image the cancer and then radiate them. It's just like we were talking about with iodine used to image cancers in diagnostic radiology, and then using that to enhance the effect of external beam radiation therapy. So it seems to work, at least in theory, and this is all pretty new, so 2017. A lot of this is new, continual work being done on modeling at least, and then eventually we'll get around to doing clinical work with these. Here's a demonstration for cervix cancer cells. Now, these are just cervix cancer cells. We put cervix cancer cells at different depths in tissue equivalent materials, and we look at the effect of the radiation. So, is there an enhancement? 1 means there's no enhancement. More than 1 means there's an enhancement of the biological effectiveness. And sure enough, as these radiations go deeper into tissues, now a typical cancer in a patient is not on the surface, it's deeper in the tissue. What happens? Well, when the radiation goes deeper into the tissue, it loses its energy, it becomes less energetic. Lower the energy, the more photoelectric effect you're going to get. So you would expect that there would be an increased effect with depth. And interestingly, there's an increased effect with depth, and this happened to be with 50 nanometer spherical gold particles at this density. And what's really interesting is there's even a higher increase with flattening filter-free beams. These are flattening filter-free beams. Interesting. So with flattening filter-free beams, for some reason or other, the authors of this paper didn't explain it, but they show the data that shows that you actually get an increased effect, maybe an extra 20% increase in effect with flattening filter-free beams. So this is exciting new development. It's all physics, a lot of people working in it. I'm sure a lot of people doing their PhD theses in physics, medical physics groups, working on this, trying to improve it. And then there's going to be quite a few clinical trials before this ever really goes into operation. So let me summarize. Physics has played a very important role in making modern radiotherapy more effective and more efficient and safer. So it's better able to cure cancers, less likely to cause damage to normal tissues. Future applications of physics, such as, I'm only mentioning a couple, there are lots more, but we haven't got time to do all those, such as use of ultra-high dose rate, flash, radiotherapy, and nanoparticles look promising. I haven't even talked about other applications of nanoparticles. For instance, I mentioned they were good for imaging, but they also can be good for delivering other agents to the cancer, like chemotherapy agents to the cancer. So, and a lot of research is going on there at the same time as this is. Okay, well, my voice lasted. I can't believe I made it. And I didn't even have it. And I use water, not tequila. Amazing. Tonight I'll try tequila, see if that works.
Thank you for the great talk. Do you see any correlation between those countries in which there are heavy ion treatment systems and the establishment of the good establishment of medical physicist training programs and certification?
Not really. Interestingly, that's a very good question. The one country where we've got most heavy ion facilities in the world is Japan. And Japan hasn't even had an organized medical physics group, let alone lots of training programs, until fairly recently. I know I was looking at Japan because I used to be Secretary General of the IOMP, the medical physics group. They were so disorganized I couldn't get them to form a medical physics group. And trying to get the educational programs that taught medical physics. So actually, no. Germany, there's a couple in Germany, and yes, they have good medical physics training. But interestingly with Japan, and China, I think China are beginning, and they really haven't had traditional medical physics training programs. They're beginning to get them, but not yet. So it's interesting, no.
A couple of times you said that hypofractionation will mean, since it means shorter treatment times, it also means more efficiency in the service because more patients can be treated. But the treatment itself becomes much more complex. Safety gets much harder to assure because now you are giving such a high dose that you cannot make mistakes. In the old times, you could be a little bit wrong.
Right.
And the tumor will always be inside the
Very
square
important
box.
point.
So that means that there must be an increase in time before the treatment.
Correct. But
Comment.
the equipment itself is used more. It's more efficient to use the equipment. The staffing that goes behind it to create the safety that we need to make sure that the patient gets the right dose and the right dose distribution is more. What does that mean? We need more physicists for that. We like that. When IMRT first started, I remember distinctly, I was running the medical physics master's and PhD program at Wayne State University at the time when IMRT first started. Immediately, we graduated 40 students on that 1 year because suddenly everybody wanted medical physicists and there weren't enough. So My physicists all got jobs, all 40 graduates, I think it was 37. All 37 graduates got jobs right away. Interesting jobs, because they were doing things like IMRT. And that's what happens. But let me agree with you that you can get into a lot of trouble with hypofractionation if you don't do it properly. When hypofractionation first started, and I mentioned this yesterday in my talk, when hypofractionation first started, people didn't increase their physics staff to do better quality assurance, and they didn't adequately research what dose they need to give those patients. They just took a guess of what dose and they got it wrong. And so hundreds and hundreds of patients got over-irradiated to their normal tissues and got into bad trouble. So you've got to be really careful.
That's exactly the reason of my question. So how do you make sure that you have these trained people to manage all?
Right. Yes. With carbon ion therapy, you don't need trained medical physicists, you need trained physicists who then become medical physicists after they've been working on developing the carbon ion therapy. You then hire them. That's how we used to run medical physics years ago. I'm going back a long time now. In fact, let me go right back. The very first megavoltage X-ray machine in the world was established where I was trained up at St. Bart, before I was trained. I'm not going back that far. At St. Bart's Hospital in London. And the engineer who was there to establish it and get it working from Metropolitan Vickers Company, when they got it working, they persuaded him to stay on as a medical physicist. And he became president of the British Institute of Radiology and the Hospital Physicists Association in England. He became but he originally was just an engineer. He only had a bachelor's degree and became president of the British Institute of Radiology. Radiologists, they're very unusual. His name was George Innes. I'm sure none of you have ever heard of George Innes because he hardly ever published any papers. He was a working engineer doing medical physics. And of course, he got physicists to come in and learn medical physics under him. In fact, I learned a lot of my medical physics from him.
I have a question about the nanoparticles and the Auger electrons that you were talking about. In order to take advantage of the Auger electrons for therapy, they must be released in the nucleus of the cell. So that means that you need to bring the nanoparticles into the nucleus in order to really be effective. Is that the case? Does the nanoparticles that are being used for these applications can get into the nucleus of the cell?
Then you have to design the size of the nanoparticles and the retention of the nanoparticles. And obviously, many of them will be outside the nucleus. And that will be wasted. That's why we don't get as big an effect as maybe theoretically we might think we would get. So yes, a lot of that is wasted, but some of it won't be. And it's free. It's free energy being delivered extra and above what you're treating the patient with your conventional radiotherapy. Okay. So a lot of that will be wasted. You are correct.
Okay. And the other, I don't know, question or comment, but when you were talking about the flattening filter.
Yes.
When you have the flattening filter, it's not only to make more homogeneous the beam, but also it's a different spectrum. You are hardening the beam when you are using the flattening filter. Correct. I don't know, for example, when Correct. You don't have the flattening filter, when you see the difference is because the spectrum right. of the X-rays is different in each right. case.
When you put a flattening filter in one of these cones in the beam, you actually harden the beam. You take out all that soft energy radiation from that beam. And when you remove the flattening filter, the beam is much harder. It's more, so you get a better depth dose distribution without the flattening filter in there. So you get an advantage there. So there are added advantages I didn't mention. Right.
Other questions? So I have one with, but you mentioned it, the question of dosimetry when you have this fast
Yeah,
flash dose.
Yes.
So we have to increase thousands of gray per second. That was the graph
Yes.
that you show. But the concern is, you mentioned it, is the dosimetry. So that means we have to redecide the way we make dosimetry?
Yes.
Because actually, I think I reviewed a paper for a group in Germany. They are trying to make new ionization chamber because the model, that is the ionization chamber
Right.
that I use, like a conventional in the clinic to calibrate the beam. Actually, with this kind of beam, this chamber, they are completely saturated because there is no enough time, because the dead time for
Right.
to connect the electrometer to get the charge collected is a
I
A flash of signal.
kind of doubt the ionization dosimetry is going to be used. I think we'll use something else.
but
We'll use something else. We'll use,
yeah, and there is another. If you use chemical product
Chemical,
also, the
right.
chemical also have an evolution on time.
That's
In
going to have to be studied. It's a
the
dose rate.
polymerization process that is
Right.
going on within the.
But
if you use a
probably of the
polymer
order of
material.
nanoseconds, and we're not talking nanoseconds, we're talking microseconds maybe. And maybe it's a different order of magnitude. But again, lots of studies need to be done. I don't think we're just going to do it. We need to study it very extensively. But I would think in 5 years' time, we'll be ready. Lots of people are working on it. And it looked very promising. Yeah.
Other questions or comment?
I hope you could all understand me. Yesterday I could talk, today I can't talk.
Okay, if there is more question, we take.